Greetings, everyone. Welcome to the 197th session of the online Optom Learning Series, OOLS. And for today's session, we have with us Professor Eric Peppers. Prof is an emeritus professor in the School of Optometry and Vision Science at the University of New South Wales in Sydney, Australia. He holds degrees in physics and optometry, and much of his career has been involved in research which is related to ocular surface and contact lenses. Originally from the UK, he spent his time in various different fields, I would say, in terms of clinical practice. He has been into industry and currently probably stayed in academia. He is in Australia, where he is formerly the Executive Director of Research and Department at the Brian Holden Vision Institute, and he was also a co-inventor of silicon hydrogel contact lenses. Internationally, a very well-renowned academician, researcher, and an educator. He lectures intensively in these areas of his interest, has been awarded various awards by the American Academy of Optometry, by the British Contact Lens Association as well, published numerous papers, and has and is also an editor, associate editor of various journals, Contact Lens and Anterior Eye. He's the editorial board member of Clinical and Experimental Optometry and Eye and Contact Lens Journal. He is keen into teaching and research, and with that, he was also recognized recently by the University UNSW for his excellence in postgraduate supervision. So welcome, Prof, onto our platform. Thank you so much for spending your Sunday afternoon with us and taking us through your views about dry eye and how can we go about estimating the prevalence. So welcome, Prof, onto our platform, and let me just leave the screen time to you.
Well, thank you. Thank you very much. It's great to be able to talk to everyone here. I was just saying before about the timing of these talks. Usually, or not usually, but often when I'm giving talks, I'm speaking to people in Europe or North America, and living in Australia, the time differences can be quite difficult. So it's more of a pleasure to be talking more in my own region and surrounding regions where perhaps it's not quite so crazy timed. However, if you do feel that you need to watch the replay or watch the video, that's fine too. It's a thing that I would do in these circumstances. But for those of you here in person, then welcome, and I hope we can tell you something useful and helpful. My email address is here at the bottom, and if anybody does have any questions after the talk and you'd like to email me, please feel free to do that, and I'll try and answer them there. So the talk today is about the prevalence of dry eye, and just before I begin, I've got a few disclosures and acknowledgements that I need to tell you about. These are the companies that have given me money in recent times, but none of those funding opportunities relate to the information that I'm talking about today, so I don't have any conflicts. And at the bottom, there's just an image acknowledgement there, just about the images that I will be using and sharing with you. Okay, so the talk today is about prevalence, and specifically the prevalence of dry eye. And so just to remind you of the definition of prevalence, it's the proportion of a population that's affected by a condition or a disease at a particular point in time or over a specified period of time. So, for example, if we have 100 people, as we have in this situation here, and 20 of those people are affected by, let's say, dry eye disease, then the prevalence would be 20%. And of course, prevalence should not be confused with incidence, which is the number of new cases that occur in a population over a specified period of time. So we're not talking about incidence, we're talking about prevalence. Now, why should you care about prevalence? Why would it be important to any of us, but particularly people who are in practice, optometric or ophthalmological practice? Well, I think prevalence does give an indication of the burden of disease that exists in the population. So, for certain people who are economically concerned with diseases, and that can be governments or local health authorities, and of course ourselves as practitioners, it gives us an indication of how many people really in our society might be affected by this particular problem. And that helps us, I think, as practitioners to determine the scope of practice that we want to have. So conditions which are more common than others obviously are more likely to come through our doors, and we're more likely to see those people and those kind of conditions. So we can tailor our practices to dealing with those kind of things because we're going to be seeing them more often. We may decide that we want to specialize in some areas of practice, and knowing the prevalence gives us an idea of how many people we might like to see. So we might decide to be a dry eye specialist. And that's not any use, of course, if there aren't that many dry eye people around. So it does give us an idea of how we can determine the scope of our practices. And of course, that means we can educate ourselves towards those things that are likely to be more common, and get the right sort of equipment and resources to enable us to diagnose and treat those conditions to the most effect. So prevalence is important for all these things. It has another important aspect, though, and that is that prevalence does affect the accuracy with which we can make a diagnosis. And I'll talk about this later in the talk, but it's an underappreciated aspect of prevalence, but it's a very important one. So this is kind of why it's important for us to worry about. So here's our first poll question. So I'd like to ask you to estimate what you think is the prevalence of dry eye as far as you're concerned. So on your own experience, what do you think is the prevalence of dry eye? There's no rights or wrongs here. It's just what you think.
I think almost half of them, 48%, think that it is more than 40%. And the next highest would be 31 to 40%. So toward the higher side is what I would say. Yeah.
Absolutely, yes. So this audience thinks that dry eye is pretty prevalent disease, which is interesting. And as I said, there's no rights or wrongs here, but it's interesting for me to gauge the experience of people who are listening to these kind of talks. Okay, so that gives us an idea of what you think in the audience at the moment. So let's just move on when my slides change, which they will do in a minute, I think. Just get a bit stuck. Here we go. Yes, so dry eye is an area that has increased in its profile over the last 40, 50 years or so. The first published prevalence study was back in 1995. And since then, there's been about 150 studies which mention prevalence in their title or their keywords. And so as you can see from this little graph here, the numbers are increasing quite dramatically. So there's a big upswing in the number of prevalence studies that are being published. And that indicates the relative importance, I think, to our community of dry eye, but also the awareness of dry eye that's spreading across the world. The problem is that the reported prevalence range in those studies goes from 3% up to 70%. And so that includes the range that all you guys said. But actually that wider range isn't all that helpful because we don't know where in this range of things the real number might be. So we like a number that's a little bit more useful to us. So how do we make a relevant estimate of prevalence? As I said, there's lots and lots of different studies, and it would be really great if we had a way to combine data from several different studies to give a more useful estimate, an estimate that relates perhaps to our own personal situations. And I'm going to explain how I do this, and just to give you an introduction to this, I want you to just think about this situation. So I want you to imagine that there are two teams playing, could be football, it could be rugby, it could be any game, Australian rules, whatever game, hockey, doesn't really matter. But one team plays in red and one team plays in blue. So I want you to just think about this and just think about who do you think will win today? You can't have a draw. And of course, most people would say, well, it's 50-50. So if we were to ask 100 people, roughly half would say red and half would say blue. Actually, experience tells me that there's a slight bias towards red. There's actually research which suggests that teams that play in red actually win a bit more often than teams that play in blue. So that's interesting. So it wouldn't surprise me if we did this survey and the numbers came out a little bit like this. So 55 red, 45% for blue. Next thing I want to do is give you a little bit more information. So now I'm going to tell you that the last 10 times these two teams played one another, the blue team won 9 of those 10 times. Now, if I ask you who you thought was going to win, I suspect you'd give me a slightly different answer. And so what happens in this situation? Well, we think about the original situation, perhaps, as our existing belief about the situation. And it's roughly 50-50, slight bias towards red. When we add some data to that, we give you some more data, it changes your belief. And it changes your belief in a way that might look something like this. So now with this 9 out of 10 bias, we might swing to saying, well, you know, it's probably 9 out of 10 times likely that the blue team will win. So this is a system of thinking which is very common. It's called learning, basically. We do this every day. We take new information and it alters our beliefs, if we're an open person, to a new situation, which includes the existence of more data. Now, this is an example of something called the Bayes price rule, and Bayes was a clergyman, a religious person back in England in the 17th century, 18th century, actually. So this is Thomas Bayes, and he developed this thing called the Bayes price rule, which basically says that your current belief is modified by data to give you a new belief. And Richard Price worked after Bayes died to formalize this, so it's often known as the Bayes price rule. And some people actually think that Laplace did this as well some years later. It doesn't really matter, but it's usually known as the Bayes rule or the Bayes price rule. So what these guys did, they gave mathematical names to these components. So they called your current belief the prior, they called the data the likelihood, and they called the new belief the posterior. And so we can mathematically combine all these things with some extra bits and pieces to be an expression of how we change our beliefs based on the acquisition, the knowledge, new knowledge that we get. So how can we use this in our situation, in our situation of prevalence? Well, if we think about what prevalence is, prevalence only exists in the range of 0 to 100%, or 0 to 1, if you want to put it in decimal terms. So if you have a sample of people, and we've got n people, and the number who have the disease will be alpha, and the number that don't have the disease is beta. So alpha plus beta equals the total sample size, so n equals alpha plus beta. And the prevalence is the numbers with the disease, that's alpha, divided by the sample size, which is alpha plus beta. So we can represent prevalence in this way, and actually, mathematically, we can represent this situation by something called a beta distribution. I'm not going to bore you with the mathematics of the beta distribution, but it uses these two numbers, alpha and beta, to create a probability distribution which represents the situation. And in this case, that situation is prevalence. So just to show you this in a little bit more detail, I'm going to take the first prevalence study that was published by Hikichi in 1995. And in that study, they had 2,127 people. Of those people, 359 had dry eye, and 1,768 did not have a dry eye. So alpha is 359, beta is 1,768, and the total sample is 2,127. So the prevalence was 16.9%. Now, when we plot the beta distribution for that, it looks like this. It's a nice symmetrical curve, which actually is peaked at the prevalence data, prevalence point. So the peak of that curve sits nicely at 0.169, which corresponds to the prevalence of 16.9%. So that's a nice little property of the beta distribution. What happens if we have new data? Hikichi's data were the first. The next study that came along was that of Shine in America. So how can we combine these two things together? Well, Bayes' theorem tells us that it's actually very straightforward. All we need to do is to add the two beta distributions together, and that will give us the new distribution. So here we have Hikichi's data, the beta distribution for Hikichi, that's the dotted line here. And this is the data for Shine, which has a slightly different estimate. He estimates at about 15%, so a little bit lower than Hikichi's 17%. And when we add those two distributions together, we get this new distribution, a combined distribution, which actually has a peak at 1.6 or 16%. So the new prevalence estimate is now 16%, and it includes all the data from both Hikichi and Shine. So this process is very simple, very straightforward. And of course, we can do that for all the data that we have. And this is what that looks like. So now I've added in all the prevalence data from all the studies that I'm aware of, and it looks like this. You can see, first of all, it's very peaky, very sharply peaked. This is Shine here, this is Hikichi here, and this is now the distribution for all the data that we have. 67 studies in that new estimate for distribution, about 600,000 people, if you take all those studies involved, and the prevalence estimate is 11.6. So that's the global prevalence of dry eye disease is 11.6%. Now, those of you that are getting a little bit upset because you estimated things much higher than that, needn't worry, because, of course, this is a global estimate, and it takes into account all the data. And I really mean all the data. So all the studies that are included in this have different geographical locations. They have different diagnostic criteria involved. They involve both sexes and all ages. So it's very, very much a composite estimate. So don't get too worried if you said things were higher, because your time's going to come. Okay, so this is our global estimate of dry eye disease, and I hope you followed a little bit of how I calculated this number. But it is very important when we're doing these kind of processes to screen the studies to make sure they're relevant to the question that we're asking. So basically what we need to have before we do this process is a hypothesis or a research question, or simply something that we want to know. And that might be quite simple. It might be something like, what is the prevalence of dry eye symptoms in men, middle-aged men, aged between 45 and 65 years old, who live in Oceania, Australia, New Zealand, and the area around there? We might want to know the answer to that question. And so using this process, we can evaluate the data on that basis and produce a result. So there's an easier way for you to do this, which is, of course, that I published these data in a paper. So you could just go and look at the paper. And in the paper is a table like this, which has a summary of all the relevant information. So if we wanted to answer the question that I just asked here, and I've magnified the table a little bit. So the prevalence of dry eye symptoms in males aged between 45 and 60 years old in Oceania is here, Oceania, 40 to 65, and the prevalence is 14.4%. And there were 3 studies that contributed to that information. So that gives you an idea of how confident we can be about that number. If you wanted to know the corresponding number for women, that's in the next box, and that's about 16.6%. So you can see how we can get this information by looking at these tables. If you wanted to ask the same question for Europe, though, we find that for men, there's actually no data. Nobody's really done a study which identifies the prevalence of dry eye in this age group in Europe. So not for men. They have done for women. It's about 18% for women, but men, no data. And that's one of the problems, is that the studies that have been done don't necessarily cover the entire range of things that we might wish to know about. So that's one way to get the information that you might need. And if you're keen enough, of course, you can go back to the source data and you can do the calculations yourself. And I've kind of made that a little bit easier for you by this spreadsheet. But there's a couple of people who've published prevalence data and summarized prevalence data. The first group to do that was Fiona Stapleton and colleagues in the TFOS Juice 2 epidemiology report, and they produced tables of prevalence data up to about the beginning of 2017. I took those data and added about another 20 studies. So at 2021, there's now, as I say, about 67 studies. And this spreadsheet here, which you can look up online, if you go to this URL here, you can access this spreadsheet. And you can filter the data on any of these criteria. So region, age, or sex, and you can work out the prevalence. In fact, the spreadsheet will work out the prevalence for you for all these things. So you can query the data for any kind of question that you want to answer. If you're interested, it will also plot the beta distributions for you as well. So here's a way you can answer the question of prevalence for really anything you like. One of the problems with doing this is, of course, it's always out of date. So even though this was up to date in the beginning of 2021, there's been 5 or 6 more studies since then, which aren't in the existing spreadsheet, but I'm trying to get the journal to update it every couple of years. So hopefully it will be fairly up to date as we go forward. So that's how to do some prevalence queries. So now let's look at some of the things that come out of the data, out of the prevalence data, that might be interesting or useful to look at. And the first thing I want to talk about is actually location. We've already kind of suspected that there's a fairly wide variation in prevalence reporting depending on where you are in the globe, across the globe. And you can see this variation is really quite enormous. In North America, prevalence is 5%, about 5%. Whereas in Africa, it's about 70%. And around the world, there are various other figures. So Europe, about 14%. South America, about 15%, about the same, and roughly the same in Oceania. In Southeast Asia and Southern Asia, a little bit more. So you guys are getting a little bit closer to the mark here with 30% in this region. So these are the summary numbers that come out of the data, looking at it using these techniques. One thing I did want to say, though, was the numbers that you do get when you do this depend a little bit on the methodology. And one of the reasons why this North America figure, I think, is so low is because several of the prevalence studies conducted in North America use a method where they query big databases. So they'll take a military database, perhaps, or an insurance company database, and they'll look for people in those databases that have dry eye. Now, because those databases are often created for reasons other than diagnosing dry eye is a bit secondary, so the numbers may have a different meaning. But what happens with these databases, which are very large, is that the prevalence of dry eye in these databases is rather low, but because there's so many people in the database, it has a very big effect on the overall estimate. So that's why one of the reasons why I think North America comes out with a relatively low prevalence. Just as an exercise, I did a study, a calculation where I removed all those big databases out. I took out every study that was over 10,000 participants. And when you do that, you get a North American number, which is 17%, which is much more similar to Europe, South America, and Oceania. So I think that 5% figure arguably might be a little bit on the low side. But that's location. What about age? I think most people would think that dry eye increases with age. And while that's largely true, I think there is substantial disease in the young. So people between about 20 and 30 years of age have substantial prevalence of dry eye disease. But then it goes quiet for about 20 years. So between about 30 and about 50, it becomes much less common. So there's this quiet period in that just 2-decade period, after which it increases more or less linearly as we continue to get older. This is the black line here is for symptoms. And the same thing more or less happens for the signs of dry eye disease as well, although there are really no data for people under about 40 years of age. So both signs and symptoms do increase after about 40 years of age, but there's an excess of signs over symptoms. And I think that's a little bit interesting because it kind of means that there are people around, particularly older people, who may have signs of dry eye, but not have symptoms of dry eye. So the practice that many people advocate of prophylactically treating someone for dry eye because they may have signs, I think you need to think about that a little bit carefully, because clearly some people can have signs of dry eye with no symptoms and continue like that for quite long periods of time. So prophylactically treating those people may not be the right thing to do. In fact, there's some evidence to suggest that elderly people actually produce more tears, more aqueous tears, to compensate perhaps for the decline in other aspects of their dry eye physiology. So I think that's something that's worth thinking about. What about sex? Well, I think most people expect there to be more dry eye in females than in males, and that's borne out by the data. Across the globe, the numbers are like this. So 9.2% for females, 7.3% for males. The reason why these numbers are smaller than the overall estimate is because not all studies actually divide their samples on the basis of sex. So these studies contributing to these numbers may not be the same studies contributing to the overall number. But you can see this differential is pretty well maintained across the globe. So whilst the overall numbers will change, the differential between males and females is pretty well consistent around the world. So yes, women do tend to have more dry eye than men. What about time? This is interesting because people clearly often say, so is prevalence increasing? Is dry eye increasing with time? And one of the things we can do is to look at this over time by adding studies in on a year-by-year basis. The dotted line here is the point prevalence. So this is the prevalence at each age, at each year, just using the studies for that year. And the black line is a rolling prevalence where each point includes the data for the previous point. And you can see the prevalence of dry eye on a rolling basis is actually reducing. These data are from East Asia, which has the longest series of data available. And it looks like in that region, the prevalence is actually diminishing to the extent that actually the point prevalence and the rolling prevalence are about the same in the last year for which we had data, which was 2019. Who knows what's going to happen during and after COVID? Everybody, I think, is expecting a bit of a spike, but whether that will eventuate remains to be seen. The next thing that really does affect prevalence is the diagnostic criteria that the person doing the study chose to use. Those studies where they looked at symptoms as the diagnostic criteria report a prevalence of about 9.7%. Whereas if you use the DEWS-2 criteria, which I'm going to talk about in a bit more detail in a second, you get a higher prevalence of about 26.5%. So how you define dry eye, how you decide on who has dry eye does affect the prevalence. And that's going to be important for the next part of the talk, really, because as we've said, the diagnostic criteria affect the prevalence estimate that you get, but also that prevalence estimate affects the diagnostic accuracy of the test that you're using. So basically, prevalence affects how good you can be at diagnosing dry eye. And the second part of the talk is going to be a little bit about that and give you more information about what I mean by that. So let's just think about the diagnostic process. When we do a diagnosis, it doesn't matter whether it's dry eye or whatever it is, what we typically do is administer a test. And if the test comes out positive, then we start treatment. If the test comes out as being negative, then we send the patient home. Unfortunately, it's not that simple because no test is 100% accurate, and there are in fact more than two outcomes. So for any test, there are four possibilities. And those four possibilities are that the test can identify somebody that actually has the disease, so that would be a true positive. And it can also identify somebody that doesn't have the disease, which is a true negative. Those are the two things that we want. Unfortunately, it also may come out and tell us that the person has the disease when they do not. That's a false negative. Or it may say that they have the disease when actually they don't have the disease. That's a false positive. And these two things are problematic. First of all, false positives are expensive because it means we treat people that have no need to be treated. Whereas false negatives are dangerous because it means we don't treat people who actually do need to have some kind of treatment. So they're not things that we really want to have. And so the likelihood that a person who tests positive really does have dry eye depends on the behavior of the test and the true positive rate and the true negative rate. The true positive rate is sometimes called sensitivity, and the higher that is, the better. And the true negative rate is sometimes called specificity. And again, the higher that is, the better. So for all tests, we want to have high sensitivity and high specificity. But there are other factors as well. And of course, given that the talk's about prevalence, it's not surprising to find that prevalence is an important factor. Just to show you what I mean by this, imagine a test which had a positive rate, true positive rate of 90% and a true negative rate also of 90%, which is quite a good test, a very good test. But the prevalence of the disease in this population is about 50%. Now, this situation would mean that 5 of those people would be shown to be false negatives. So they would be actually have the disease, but actually shown not to have the disease. And conversely, there'd be 5 false positives, people who didn't have the disease, but the test said that they did. That's okay. It's what it is. It's not great, but it's what it is. If we now think about the same situation, but this time the prevalence of disease is only 1%, then those numbers mean that the person that actually does have the disease has a 1 in 10 chance of being missed, but also that there are 10 people would be turn out to be false positives. So we might start treatment on those 10 people who don't need it. So even with a good test, if prevalence is low, you could only be treating those people that actually don't have the disease. So you can see how prevalence is an important factor. Let's turn to dry eye now and think, just to remind you what tests we do use to diagnose dry eye. This is a TFOS definition, and the TFOS current guidelines say that the way to diagnose dry eye is to use 4 tests: a test of symptoms, plus a positive outcome on 1 or more tests of signs. So the symptoms questionnaires that are recommended are the Ocular Surface Disease Index, or the dry eye questionnaire, the 5-item dry eye questionnaire, and the cut-off scores you can see here for those 2 instruments. And the other tests, the tests of signs that are recommended, are tests of tear film homeostasis, so non-invasive tear breakup time, or a fluorescein tear breakup time with a cut-off of 10 seconds. A test of osmolarity using one of the various point-of-care instruments that are available. And again, 308 milliosmoles is the cutoff, or a difference between the 2 eyes of about 8 milliosmoles. And a test of ocular surface staining. So we can use fluorescein to look at the corneal staining, and lissamine green to look at the conjunctival staining, but also the staining of the eyelids and lid margins. So those criteria you can see there. So these are the tests that the TFOS workshop recommends. And the equation for diagnosing dry eye is this one. So the presence of symptoms plus 1 positive sign, whether it be non-invasive breakup time or fluorescein breakup time, osmolarity or ocular surface staining, symptoms plus 1 of those equals a diagnosis of dry eye. So that's the diagnostic criteria that is recommended at the moment. But what is the quality of making a diagnosis on this basis? So again, the question is, if a person returns a positive test on this basis, how likely is it they really, really do have dry eye? So let's think about that. And so here's our next poll question. So of those tests we've talked about, which one do you think is the most useful test for dry eye? So the poll's coming up there. So you have a vote there. So which of the tests, symptoms, osmolarity, tear breakup time, corneal staining, conjunctival staining, or something else, if you think something else is better, which one do you think is the best for diagnosing dry eye?
Majority of the attendees' ideas are shifting towards tear breakup time. So almost 60% says the tear breakup time would be the most useful test, and followed by symptoms. And then a couple of them say about the stainings in the conjunctiva and corneal as well. Yeah.
Yeah, very interesting. So tear breakup time is the winner here, followed by symptoms. That's very interesting. So let's have a look at what the data say. Again, I'll move on when I can. Just be a second or two to move on. It's got stuck here.
Yeah. Maybe you'll just have to click on the slide once, and I think it will move.
Yeah, maybe. Let's try that. There we go. There we go. So we've moved on. All right. So what we really want to do now is answer this question. So if somebody really returns a positive test, what is the likelihood that they really do have dry eye? And is that the same for all the tests? So we're going to try and answer that question. And to do that, we need to know a couple of things. For each test that we're going to do this for, we need to know the true positive rate, so the sensitivity. We need to know the true negative rate, so the specificity. And we also need to know the prevalence of the disease or condition that we're going to deal with. So I've already told you how we can calculate prevalence, and I'm going to tell you in a second how we're going to calculate the other things. But this question at the top here is actually, again, an expression of Bayes' rule. This is how Bayes' rule is stated by Bayes and by mathematicians. And it looks a bit scary, but actually, if we break it down, the first part of this is actually just a question that we want to know the answer to. So this is just, what is the probability that a person really has dry eye if they test positive? This bit here is just the prevalence of the condition. And these other two bits are just combinations of sensitivity and specificity. So you don't need to know the details, but we combine these three bits of information to answer the question, which is also sometimes known as the positive predictive value for that test. So we're going to run through that situation for each of the tests that we have. Before we can do that, though, we need values for sensitivity and for specificity. And when we look in the literature, of course, there are several different studies in each case. So we're faced with the same problem that we had for prevalence, which is that we have more than one number. So which one do we use? Well, of course, we can go through the same process that we went through for prevalence, because both sensitivity and specificity are defined in the range of 0 to 1. So we can use the beta distribution again to combine the data from all the individual studies to give us single values of sensitivity and specificity for each of the tests that we have. And these are the numbers. I'm not going to go through that. These are the numbers that I came to from each of the studies. And this should be published fairly soon, so you'll be able to look this up in the paper. But this is what it looks like there. And so using those numbers, we can then look at answering the question, what is the likelihood that a person has dry eye if they test positive? So these are the data, or coming up with the data for each single test. And I've done this at a prevalence of 11.6, which, if you remember, was the global average prevalence that we came to. Of course, the answers will vary depending on the number that you pick, but we had to pick something. So this is the number that I made the determination at. So these are the likelihoods. They're not very good. So symptoms come out at below 20%. DQ5, about 20%. OSD, 14%. So if a person tests positive on the OSD test, there's only a 14% chance that they actually do have dry eye. And I don't think that's very good. The best test, if a person has corneal staining, then there's a 28% chance that they actually do have dry eye. And the other tests are kind of scattered in this range. Osmolarity, 24%, corneal staining, about the same. Breakup time, about 20%, non-invasive breakup time, and fluorescein breakup time, about the same at about 20%. DQ5 seems to be a little bit better than OSD, which is interesting. So if you're choosing between these two on the basis of the information that exists, DQ5 seems to be a little bit better at predicting dry eye than the ocular surface disease index. So these are the single tests, but remember that the DUCE2 criterion, and here it is again, said the dry eye equation is the presence of symptoms plus one positive sign. So it's not saying you should look at a single test, it's saying you should combine at least two tests together. And so we'd expect that to improve things, and indeed it does. So these are the numbers for the OSD test combined with each of these individual tests of signs. And you can see these numbers are a little bit better than the individual test numbers, but actually not a lot, not massively better. So the best combination now is OSD with corneal staining, and that's now about 33%, which is a bit better than before, but still not great. Actually, we can improve things a little bit more by using the DQ5 outcomes with each of these things. And one thing you'll notice is that the relativity doesn't change. The numbers change a little bit, but the relativity is always the same. It's always the same ordering. So corneal staining now comes out at about 42% combined with OSD. So 42% of being correct if you have a positive result on the DQ5 and a positive result with corneal staining. So even with the best option, almost 60% of our patients might be diagnosed or misdiagnosed with these criteria, which isn't very good. And it actually seems almost like it would be cheaper and better to just toss a coin. So there must be a way we can do better. And in fact, if we think about what JUICE 2 actually said, they said you should have symptoms plus at least one sign. So they're not saying you should rely only on one sign. If you've got more signs, then that should be better. And indeed, when we add in more signs, we do get an improvement in results. I'm only showing you the dry eye DQ5 results here because they're always the best. And we're combining now with these combinations of two tests. So conjunctival staining and breakup time, we're now better than 50%. And if we go up to the top of this list, then either corneal staining and osmolarity or conjunctival and corneal staining come out at around about 65%. It's getting a little bit better now. So combining these tests gives us a better chance of being correct at the end of the day. I think this is interesting to see how well conjunctival and corneal staining come out of this, because we might think of these as being the low-tech approach. We don't need expensive osmometers or tear breakup time, non-invasive tear breakup time equipment. We can use very simple techniques, corneal staining techniques, and combined together, these two actually give us quite a good outcome. So low-tech techniques can still be very effective. So ocular surface staining, which is a technique using fluorescein staining for the cornea and lissamine green staining for the conjunctiva. Generally, we do these things together, so you might even consider them to be just one test. But the criteria are often spoken about as being staining of the cornea or staining of the conjunctiva, but I like to suggest that be changed to staining of the cornea and staining of the conjunctiva. And if you make that little change, then you get a much better diagnostic accuracy and with very, very simple methods. So I'd like to suggest that that's something you consider doing. And of course, we can continue this process. We can add in even more tests. And if we add all the tests in together with the DQ5, then a positive outcome on osmolarity, breakup time, corneal staining and conjunctival staining now gets us up above about 90%, which isn't too bad. So by doing everything and getting positive outcomes, we can improve our chances quite a lot. Now, I need to remind you again of the importance of prevalence, because we did this at a prevalence of about 11.6%. And this curve just shows you how the probability of getting a correct diagnosis changes as prevalence increases. And I've done that for the worst combination of these two tests, which is OSD and tear breakup time, that's this line here, and for the best combination, which is DQ5 and corneal staining, which is this line here. And I've also put in DQ5 with conjunctival and corneal staining, which is the dotted line. And you can see the difference between the best test and the worst test depends quite a lot on the prevalence. The poorer tests are actually less sensitive to prevalence, but that's not a good thing, because it means that the chances of us being correct get better much more slowly. So this curve doesn't increase as quickly as this curve. This curve goes up very rapidly as prevalence increases. So from 11%, which is about here, up to about 25%, which we were seeing in some of the global data, the prevalence increases, the likelihood of being correct increases quite rapidly. So choosing the best test it is still important, but depending on the prevalence, it's more important for some tests than for others. So just to sum all this up for you, in terms of prevalence, knowing a relevant value is really important, but that value is going to depend on where we are, where we live, where we practice, the age of the people that we're concerned with, their sex, and the diagnostic criteria that we're interested in using. And that might be also dictated by the survey methodology that's in some of the studies. But combining data across several studies helps us to make these estimates and to derive estimates that are relevant to our situation. And so I hope I've shown you how to perhaps access some of that information in your own circumstances. When we're diagnosing dry eye, the likelihood of us being correct in our diagnosis depends on the prevalence, but also on the tests that we use. And there's a hierarchy of those tests. So the most efficient tests are corneal staining, conjunctival staining, and the least efficient are symptoms. And that's interesting because I was a believer that symptoms were one of the better indicators. And it turns out that that may not be the case. But remember that no single test is really very good on its own, and they're much better when combined with other positive tests. So multiple testing improves our chances dramatically. And if you're going to combine two tests, then conjunctival and corneal staining is particularly effective and is particularly easy to do. So I would recommend that as one of the primary indicators that we use. But generally speaking, the more tests you apply, then the better it is. And as Dolly Parton said, less is not more in this situation, more is more. And that absolutely applies to the dry eye situation. So that's it. So thanks for listening. I hope it's been helpful and useful. And if there are any questions, then I'll try and deal with them. But that's it for now. Thank you.
Thank you, Prof, for that really clear presentation. I think this is really something which can be applied in various conditions as well. I mean, you spoke about dry eye and made it so easy, but I think this could be applied with other health problems as well, where we can look at how prevalence can affect probably most of our decision making as clinicians when it comes to helping patients. So thank you so much for doing that for us. To the attendees,
yeah, absolutely.
Yeah,
I was just going to say, this totally applies across the board. It's not just for dry eye. It applies to any condition, anything that you test for. It's the same basic conundrum. Yeah.
That's right. Yeah. The question says is, in terms of the diagnostic criteria, I think you did cover up in the end, but just to reinitiate the point, because this came in early. In terms of the diagnostic criteria, if we are based in a situation where we are into a clinical setting and don't have much of the equipment, what would be the best tests which we can use to kind of get to the value? So if you can just reinitiate the point which you made.
Yeah. And it's really useful and helpful that it's simple things like staining, corneal and conjunctival staining, which I think all of us can probably do to some degree. So you don't need expensive equipment necessarily to make these diagnoses. One of the most useful things is a very simple test like corneal staining, conjunctival staining. So yes, I think we made that point, but it's worth reiterating. And I think just to clarify, because the TFOS-DUSE-2 report is a little bit vague on this. It doesn't really say what combination of staining you should do. And it's not an omission, but I think they could have been a little bit clearer. So I think the numbers say that you need conjunctival staining and corneal staining. If you get both those two things simultaneously present, then that's very predictive of dry eye. So I think those two things together would be the key marker.
That's right. And I think one of that, we routinely do it for our patients when we are doing ocular health. So it's not just something doing an additional test, but it's more like routine tests, which you can do it, more efficiently to look out for those spots, 5 spots or more is what is the criteria. So it's not something which you are doing specially and you're going to help your patients.
Totally. It's a very routine procedure and it's actually quite powerful. Actually, just while we're talking about that, if I might just return to symptoms just briefly, because as I said, I was a believer that symptoms were quite powerful in this respect. But I think one of the things that this shows us is that when you do something like an OOLS test or a DQ5, it doesn't only react to dry eye, it reacts to anything about the eyes that might be uncomfortable. And that can be other things, like, for example, binocular vision disorders can create symptoms which mimic this. I had a postgraduate student, Danny Tillier, whose PhD was about this, And he showed that binocular vision problems register on an OSDI questionnaire. So that's part of the problem here, is just because an OSDI says, yes, this is symptomatic, the symptoms aren't necessarily just coming from dry eye. It can come from other places as well. And I think that's why symptoms questionnaires are not as diagnostic as we might think.
Yeah, they probably supplement the diagnosis and help us to look at it.
For
right?
sure.
Yeah.
For sure.
Yeah. The other question.
Yeah, go ahead.
Yeah. The other question is asking about the usefulness of the tear meniscus height. I think we have been doing this for quite some time, but there is no mention, I think, of this in the TFOS. So any thoughts over that in your experience?
Yeah, so in terms of tear meniscus height as an out-and-out diagnostic criterion, I haven't looked at that, so I'd need to look at different data sets. So I don't know as a primary diagnostic procedure, but what the TFOS guidelines suggest is that tear meniscus height is a measure of tear production. And I think the guidelines tend to suggest that once you've made a diagnosis of dry eye, you can then use a supplementary test such as tear meniscus height to decide whether it's an aqueous deficient dry eye or an evaporative dry eye. So it's one of those supplementary tests which you might apply to refine the diagnosis so that you can decide on the cause of dry eye and then decide on the treatment plan. So I think it's useful as a supplementary method for determining, is tear production reduced? If it is, it's probably an aqueous deficient dry eye, not an evaporative dry eye. That's the kind of way that you would use tear meniscus height.
Awesome, great. And the other question is asking if you have any thoughts over the tear sample collection on osmolarity. So any thoughts over the specifics of the osmolarity test, if you could share with us?
Yeah, of course, measuring osmolarity in clinical practice is dependent, unless you work in an optometry school with laboratories like me, it's dependent on a couple of pieces of equipment that are made available by manufacturers, and they're relatively expensive. And there's 2 or 3 of these around these days. And it's a question of whether you want to go to the expense of buying a piece of equipment specifically for measuring osmolarity. I personally have a view on osmolarity. In fact, another postgraduate student of mine, Azadeh Tabakoli, did a study where she looked at how consistent osmolarity methods are, and they're a little bit variable, to be honest. So measuring osmolarity in clinical practice can be a bit variable, and most people just make one measurement. And that's not unreasonable because they're quite expensive. But if you do that, then the risks of it not being accurate are quite high. So you need to do multiple measures of osmolarity to get a better estimate. And I think that's prohibitive because of the costs. So as you can see from the analysis that we ran, osmolarity is okay as a predictive test, but doing it properly and correctly in practice, I think, can be difficult. And so, I think manufacturers probably need to listen to this a little bit and perhaps make their methods a bit cheaper so that more of us can use them in the way that they're meant to be used and they're more useful. So manufacturers, I hope you're listening.
Yeah, that's right. And I think osmolarity is very difficult in this part of the world. There are lab tests. Of course, we can do sample collections, but they are very limited in terms of doing it in the clinic, as you mentioned. So it's more like you have to take the sample and send it to the lab. It becomes a huge, costly affair. Unless you have patients who have severe dry eyes and things like that, you would probably want to do that, but not on a routine, right?
Yeah. And I think, on the analysis that we've just presented now, you get at least as good diagnostic accuracy by using staining techniques as you do by using osmolarity. So on the data that's available to us, then obviously that's an easier, cheaper, and quicker method than relying on sending things to labs and all that kind of stuff. So absolutely, I'd rely on that.
Yeah. The other question, I think, is kind of connected again when we are talking about the staining. Would you like to give us any tips on how to use these strips? Because both fluorescein and niacinamide green are used in clinical practice. Would you want to share with us how best or efficiently we could use them?
Yeah, both of them. So, on the basis of the information that we have here, the information that we get from each of those things adds together to give us a better idea of what's going on. Of course, we typically use fluorescein to look at the cornea, and lissamine green to look at conjunctival tissue because of the way that they work. But the ocular surface as an entity is affected by dry eye as a whole. So the manifestations of ocular surface damage that might be reflecting the inflammatory situation that's going on in dry eye tends to be a global in the sense of the eye globe, global thing. And so if there are those ocular surface damage processes going on, then it's manifesting both on the cornea and the conjunctiva, we want to know about that. So we would use, or I would suggest that you use both fluorescein staining and lissamine green staining within the same consultation and looking for a positive outcome with both those things. If you see both conjunctival and corneal staining, then you're probably on your way to a successful diagnosis of dry eye, assuming that's what you're looking for. Of course, they may be responding to something else, and you need to be aware that other things cause corneal and conjunctival staining as well as dry eye. So you always need to be differential diagnosis aware.
That's right. And would you want to have a preference on which one should we put in first, or you would prefer to put them together? Any thoughts on that?
Yeah, that's a good question. I don't think it really matters, and I'm prepared to have somebody argue with me on this. I think most people would put fluorescein in first, followed by lissamine green, but I don't really think it matters. To be quite honest. So yeah, of course, lissamine green does not fluoresce. Fluorescein does fluoresce. So you're looking with different lighting. So you're looking with white light, and then some kind of blue filtered light. So the way you look is different, but I don't think it matters which one you put in first. The thing I would say about fluorescein, though, is that the peak fluorescence that you get changes over time. So if you wait too long with fluorescein, then the brightness of fluorescein will diminish a little bit. It's quite a long time. It's a matter of minutes. So, it's not that critical. But if you're looking at lissamine green first and then fluorescein, you might find that fluorescein drops off a little bit. But it's really not, such a long time that it matters greatly, I don't think.
Right. And I think we'll take one last question. And this is more regarding the future, I would say. Would there be a possible gold standard test for dry eye disease diagnosis? We see a lot of instruments coming up to do all the measurement, but what's your thought on having a single gold standard test for dry eye diagnosis? Do you think that's possible?
Yeah, it'd be nice, wouldn't it? It'd be really, really nice. I think the key to answering this question is to understand the nature of dry eye disease. And if you go back to the definition, it starts by saying dry eye disease is a multifactorial disease. And the fact that it has multiple causes and multiple inputs makes it difficult to imagine a single test that would reflect all those multiple inputs. So I think it's probably unlikely, but you never say never in this world. So while it's unlikely, I think it's possible, but I think it's going to be tricky because of the multiple things it would have to indicate. So yeah, great. If you've got one, let me know.
Yeah, that would make all of our lives as clinicians very easy. So you just click a button and you get, okay, this is dry eye, right? Awesome, great. So I think with that, thank you so much, Prof, for sharing that with us and taking us through a lot of really important aspects. And I think as we talk, this is not only just the dry eye part. You can apply this on any of the healthcare issues, myopia, diabetic retinopathy, anything like that, and calculate the prevalence and use that information into clinical practice for better outcomes for our patients. So thank you so much, Prof, for sharing your Sunday afternoon. Yeah,
my pleasure. Hi everyone. Thanks for attending. Thanks for listening.
Yeah, we do have session plans next couple of weekends. Until then, take care, be safe, and I hope to see you in the next session. Bye-bye. Thank you, Prof.